Welcome to my channel. Thank you for stopping by. In this video, I'd like to show you guys signal from this model. This is a 0.7 Tesla BBMPulser 2B1 model. Some of you have been asking to see the signal from 2B3 model, which is 4 times faster. This is a slower model. This one almost never overheats. You can use it for many hours non-stop. That's the little advantage of this slower version of this BBMPulser 2B3 model. So my setup is follow. I have a high voltage probe connected to the coil, basically across the coil. One positive connects to the capacitor bank on plus, and the second lead right here connects to the thyristor where the other wire go. And so when I energize it, I will look on the scope. We're gonna see a pulse which coil receives and how it resonates, and we can see and calculate how many times it resonates and length of a signal. We'll be able to see it on the scope. So let's take a look. Right now we're on 0.3 Tesla. This is the pulsation rate, and here is the pulse. So on the pulse, right now we are at 1 microsecond per deviation per this square. So it looks like it would resonate about, let me catch it and I'll turn it off so we can talk about this. Looks like it would resonate about 8 times. 1, 2, 3, 4, 5, 6, 7, 8 until it becomes a DC pulse. DC pulse, 1 square right here is 1 kilovolt, and this capacitor bank is 1.3 kilovolt. So we are about half a kilovolt here as we start DC pulse. So the pulse will have AC, which alternating current between plus and minus, but it only actually alternates here. This is where it starts, and then it alternates to the negative, and then goes positive, and then again to the negative a little bit. And so this is basically DC pulse because it's above this line here, so it fluctuates. It's like a pulses on a DC with a frequency of 600 nanoseconds long per each pulse, per each cycle, and that converts into 1.6 megahertz frequency, and we'll have about 8 cycles in here before it turns into DC. DC is direct current. So right here it will stop pulsing because this is on a DC side, on one side, so it turns from alternating current into pulsation, and then from here it becomes like a steady output. And this steady output, if I zoom it out, it lasts, it kind of goes here to the bottom, so the whole from start to finish it's about 50 microseconds long. Let's catch the whole signal. Okay, let's take a look. So we are at 20 microseconds per deviation. Let me zoom it out to 50 microseconds. So we're at 50 right now, and if I look from start to finish, it's about 50 microseconds long. So in the beginning we'll have some fluctuations, and then it turns into DC pulse, and then it lasts for about 50 microseconds long. So that's on a low, and as I increase the intensity to higher, the signal will change. It will start resonating 2 times. Let's take a look. After 0.4 Tesla, I gotta zoom it in so we can see the details. Here we are. We're 0.5 Tesla, 0.6 Tesla. Let me catch this signal. There we go. I'll turn the unit off, and let's talk about this as well. So as we can see here, the coil will resonate 2 times. In the beginning, it will do about 8 cycles, and then it turns into DC, direct current, and then it will resonate again around another 8 cycles. So after 0.5 Tesla, this effect will start happening. I honestly don't know why it's like that. It's supposed to be just 1 pulse, but it's double pulses. So I put everything on a paper here, and I'll read you the parameters from this. So the total pulse length is 50 microseconds long on both 0.7 Tesla and 0.3 Tesla. Resonance frequency is 1.6 megahertz on both. The resonance frequency doesn't change regardless intensity. Pulses, resonance cycles per pulse. So each pulse has a DC and AC, alternating current and direct current part inside the one pulse. As we can see, here is alternating current, then it turns into DC, then alternating again in DC, and then DC will go down. So alternating current, so we have on 0.3 Tesla, we'll have 8 cycles, 5 microseconds long. So this is 5 microseconds long and about 8 cycles here. That would be on low, and on high we'll have 16 cycles, and it will be around 11 microseconds long. AC alternating part of the pulse, and direct DC part of the pulse is 45 microseconds long on low and 39 microseconds long on a high output 0.7 Tesla. Pulse RMS, which is how much this pulse fluctuates from positive to negative. If we measure this, we can see, let's take a look here. So our deviation here is 5 volt. So because this probe is dividing voltage into 1000, and 1 square would be, because it's 5 volt, 1 square is 5 kilovolts. So we have 1, 2, 3, 4 full squares, almost another 1/5 one, and a little more here. So about 5 kilovolts, little over. 5 times 5 is 25 kilovolts. So this is on a high. On a high, the RMS is 25 kilovolts for when it comes to 0.7 Tesla, and when it comes to 0.3 Tesla, it's only 4 kilovolts RMS. This is, guys, why I am able to trigger muscles even on a low output, because of this high RMS. This is when I inject the voltage into the coil from the capacitor bank from this, it will start resonating, and when it initially starts resonating, this magnetic, it will output similar to this. It will be magnetic field, and the magnetic field is high, and that's why it's able to trigger muscles compared to SOTA. Okay guys, just wanted to show you this data from this model. If you like the video, give me a thumbs up, subscribe for more, and I'll see you in the next one.